Hello, ladies and gentlemen. Thank you for joining us today for this webinar titled Improve Structural Composite Adhesion Strength with Inline Plasma Surface Treatment, brought to you by Composites World and sponsored by Abras Training Resources and Enercon Industries. My name is Jeff Sloan and I am the editor of Composites World magazine. Today's webinar will focus on plasma treatment and composites fabrication, adhesion principles, surface preparation techniques, atmospheric plasma and flame treating trial results, and how to integrate inline surface treatment into manufacturing operations. This presentation will last about 45 minutes, followed by 15 minutes of question and answer. If you have a question, you can type it at any time during the webinar in the question field of your GoToWebinar control panel. This webinar is being recorded and when complete will be made available to you via email from Composites World. This presentation will also be made available by Abras and Enercon via email request. Contact information for our presenters will be provided at the end of the webinar. We have two presenters today. The first is Lou Dorworth. Lou has been involved with the advanced composites industry since 1978 and is a well-published author and conference presenter. He currently manages Abras' Direct Services Division. Lou is a composite materials and process specialist by trade, with experience in research and development, material and process engineering, manufacturing engineering, tool design engineering, tool fabrication, and teaching composites-related subjects. Lou is a member of SAMPE, a senior member of the SME, and a member of SPE. Our second presenter today is Ryan Schulke, Vice President Sales at Enercon Industries. Ryan earned a Bachelor of Science degree from the University of Wisconsin and his MBA from the University of Wisconsin-Milwaukee. Ryan is a member of numerous industry associations and recently presented on plasma and surface treating developments at the SPE Automotive Composites Conference and Exhibition and at the SPI Conference at NPE. Ryan leads a team of knowledgeable and surface treating application specialists. His passion for innovation and customer success is a driving force behind Enercon's plasma and flame surface treating solutions. Lou, it's all yours.
Thank you, and welcome to all of our attendees today. We want to talk a little bit about some of the fundamental adhesion and bonding terminology to get started so that we can and maybe take a look at some of the common approaches to surface preparation of composite materials that are used in the industry today. And then that'll lead into Ryan's presentation on plasma surface preparation technology. So let's talk a little bit about some of the bonding terminology. It's important to understand that there is adhesion and cohesion involved in a good bond, a good structural bond, or a good bond between any two substrates or a coating. The important area that we're going to deal with is at the adhesion interface, and the adhesion interface is very dependent upon the chemical composition of the surface of that substrate and the chemistry in which you're applying to that substrate. We're going to focus on the chemistry on the substrate, on the surface of the substrate, and we're not going to focus so much on the cohesion or the adhesive itself. So when we talk about adhesion, we're talking about those forces and mechanisms that keep the adhesive attached to the substrate. We'll go ahead and look at what some of those will be. If we're talking about a chemical bond at that surface, that is dependent upon the attraction and the attachment between atoms, defined by the behavior of their outermost electrons. These are caused by electrostatic force of attraction between opposite charges. It is this interaction in which we can modify on the surface to provide the best available surface for the adhesive to attach, and that is where we get the good adhesion to the surface or the adhesive bond. Now, under chemical bond, there's a couple of different ways that a chemical bond can can be achieved. A covalent bond is the sharing of electrons in which the positively charged nuclei of the two or more atoms simultaneously attract the negatively charged electrons that are being shared between them. If you look at different arrangements, you'll see that there are polar and nonpolar arrangements, and I have an example of that. Ionic bonding is a chemical bond in which the one atom loses an electron to form a positive ion, and the other atom gains an electron to form a negative ion. It's also called electrovalence. The term ionic bond is given to a bond in which the ionic character is greater than the covalent character. And so in the next slide, you can see an example of two different versions of a covalent bond. It's a nonpolar arrangement on the left where you have equal electronegativity that will make a nonpolar covalent bond between the two hydrogen atoms that you see here. And on the right, you see an unequal electronegative relationship, which creates a polar covalent bond, such as with the hydrogen and carbon atom that you see in this arrangement. Oops. The ionic bond, which is a bond that is formed due to the stripping or the transfer of that ion, the electron, to the other atom, is demonstrated here. Ionic bonds are formed due to the attraction between an atom that has lost the one or more electrons and an atom that has gained one or more electrons. So as you can see from the slides that I've presented so far, that we are getting into adhesive bonding at the atomic level, and that's what we're going to be talking about really when we're talking about surface treatments. Now, how do we do that? Well, you know, in the past, the idea of getting a mechanical bond, because we've always done that with metals, and also a chemical bond, but mechanical bonding being a valid way of getting a good bond on a composite has pretty much proven to be wrong. The definition of a mechanical bond basically is where you're creating some kind of surface topography or very rough surface in which you can get more surface area at a very large scale, at a macro scale, and do that in a way that you will lock in the adhesive, interlocking into mechanical features on that surface. Now, realistically, that can be done, but generally it is not done with composite materials because when trying to create some sort of mechanical surface, there's often a degree of damage that is done to the fiber in the underlying surface. Now, there's a big difference between the way a boat builder might approach a good bond compared to an aerospace or automotive person using composites. And so we do not recommend trying to achieve a mechanical bond, but a chemical bond with composite materials. So the goal for surface preparation of composite materials is to do this. It is to change the chemistry on the surface of the composite to raise the surface free energy of that composite substrate, to change the polar groups on the surface of that composite substrate so that it allows for proper wetting of the surface and proper bonding with the adhesive that it has been selected for that application. We're not going to go into detail about the adhesives, but the surface-free energy of the composite is going to it is going to react with the surface tension value of the liquid adhesive or the film adhesive that is being applied that will, as we'll demonstrate later, that will allow wetting on the surface to occur or will not allow wetting on that surface to occur. And raising that surface free energy on that surface is fundamental to getting the first step in your chemical attachment. Now, of course, we want to raise that surface energy without damaging fibers at the laminate surface. So when we look at surface free energy exchange, here is an example. You can see that the surface tension value of the liquid is greater than that of the substrate, and it beads up. Much like when you wax your car, you get very low surface free energy on the wax surface, and therefore everything wants to roll off the surface. Dust doesn't want to stick. Nothing wants to stick to that surface for a period of time until it's abraded, and that surface energy of the surface is changed, and that then allows wetting. So poor wetting means a poor bond. So what we want to do is we want to change that surface so that when we apply the adhesive and we process that adhesive, we have a good wetting value on the substrate, and that the surface tension of the adhesive will easily transfer the energy at the interface to the surface energy value, surface free energy value of the substrate. All that means is that the numbers of the liquid have to be lower than the numbers that are on the surface. So if we have a much higher surface free value on the surface of the substrate than we do surface tension value of the liquid, we're going to achieve that wetting, and that's the first step to getting a fundamental good bond. The chemistry from there is much dependent upon the adhesive itself and how well that surface has been treated. Now, this is an example of what we just saw. The contact angle measurement is a method in which you can predict whether or not you're going to get good wetting on the surface. So if the contact angle is greater than 90 degrees, as you see on the left here, then you have the bead. If the contact angle is less than 90 degrees, as you see here on the right, then you're going to have good wetting, and you're going to have a much better exchange of that electro group at the surface, the atomic electro group at that surface. So we use an instrument to look at the surface in the shop floor in a general way, so that we can look at a go no-go, if you will, for predicting whether we're going to get wetting on a surface that is compliant with the adhesive that we're using on the substrate that we're bonding to. This particular tool is called the Surface Analyst. It's made by a group called Brighton Technologies. This deposits a very small bead of water on the surface, and then it calculates the actual angle, the contact angle value that you would see. In this illustration, you see 31 degrees. That's a relatively good contact angle. What it doesn't do is it doesn't give you the calculation for the actual surface free energy measurement. For a tool that does that, you would look to something like this, the Mobile Surface Analyzer by Cruss. This one will also determine the wettability through the measurement of contact angles and calculate the surface free energy in accordance to the Owens-Wendt, Brable, Cable, Wu, Zisman, and Fowkes measure. So that standard is basically the calculation for calculating the surface free energy value. You'll see later in Ryan's presentation some of the calculations that are made using this equipment. It also allows for one-click measurement and gets results in less than 1 second, like the previous equipment. The only addition is that it gives you more information. So this gives you the ability to do quality assessment and quality control on pre-treated surfaces prior to bonding. Both tools are valuable in determining whether or not you're going to have a good surface-free energy, something that will allow wetting. Now, of course, using water or some other solvent as a standard is a good way to measure wettability. Now, if we talk about legacy or common surface preparation methods that have evolved in composites over the years, mostly in aerospace, we see that surface treatment methods range from just using a peel-ply fabric and pulling it off and bonding directly to that surface, using whatever surface exists after removing the peel-ply, and then abrasion methods. Depending upon the abrasion method, you get different results. I've got a little matrix of some testing that we've done that I'll show you. The most pre-preg parts that are made in aerospace and in other manufacturing type applications using vacuum bagging techniques, autoclave cure, that sort of thing, use peel-ply fabrics. And then after the fabric is removed, an abrasion method would be applied to increase the surface free energy. And in some cases, you do see that you get better, a better contact angle, lower contact angle, and better surface free energy values, higher strength end result. In other methods, or using the same method with a different operator, you may find different results. So abrasion is very dependent upon operation. Scotch-Brite, or the nylon abrasive type soft materials, it work quite well if used with a tool that runs at a low RPM or by hand. And the same thing with sandpaper abrasion. Grit blasting is another option, generally with alumina grit or other abrasive media that is sharp and works well. Now, of course, any abrasion method that I'm going to use is going to be very dependent upon the operator. Grit blasting is highly dependent upon operator methodology and concentration efforts. It's also kind of dependent upon having clean grit, having a clean machine, having clean air supply or nitrogen supply or other variables. It's very easy to get contamination with grit blasting just from the cabinet itself. It's got to be devoted to this process. With the Scotch-Brite, the risk of getting the nylon to melt on the surface can be seen when using high-speed tools such as a die grinder or other type of tool for trying to abrade the surface. And if you get too much friction at that interface, you'll actually melt the nylon into the surface and never get it out. So there are some downside issues associated with abrasion methods. Now, light Scotch-Briting of a previously pre-preg surface or a glossy surface is normally going to result in the best values. Sandpaper abrasion, depending upon what the substrate is, can give you, it can give you highs and lows. depending upon what the fiber form is, whether it's a fabric or a unidirectional material. Now, we don't want to get into the fabric or the fiber. Other methods are laser ablation, and of course we're going to talk about plasma surface treatment. So let's take a look at the just some numbers from some of the testing that we've done at Aberus to measure different types of methodology for abrasive techniques. At the top you can see Scotch-Brite. Now first thing I want to do is quantify. These are lap shear coupons that we make in our facility, and then we test. They're about 70 thousandths of an inch thick, 1 inch wide with half-inch overlap in the bond line. They're carbon epoxy lap shear coupons. They're made with a medium modulus carbon fiber. All surfaces have had a pre-preg peel ply removed prior to preparation. They're bonded with a 250 cure film adhesive, vacuum bagged at 10 inches of mercury, which is about 5 psi. So you have the effect of vacuum in these results. However, when you look at the Scotch-Brite and the bead blast versus the peel ply, and this is a high sol pre-preg peel ply that we use, versus an 80 grit abrasive, a wet dry abrasive, aluminum oxide, another 400 grit wet dry abrasive, you can see that you get a range of different contact angle measurements from the surface analyst. The lowest number in that matrix, the lowest contact angle, actually exists when you pull the fresh high sol pre-preg peel ply off of the surface, but it doesn't extrapolate to the highest breaking force. So obviously by abrading, we note that we have changed the contact angle measurement some by changing the physical characteristics on that surface, and we've increased the average breaking force. Now, the other thing that you might look at in this is that with other methodologies, you might end up with a fairly high contact angle, and still get a suitable breaking force, but you might end up with a high standard deviation amongst your test specimens. And that means that you're not getting consistency. So when we look at the overall ability to get good numbers, the Scotch-Brite post peel ply seems to give us the best numbers, and with a very medium standard deviation. Now, I will tell you that this is one operator doing all of the coupons. If I were to take 10 different operators and do all of these coupons with those same 10 operators, I would have widely different values, except with the pre-preg peel ply. That is going to stay very consistent, and for that reason we recommend looking at designing around numbers that are consistent and have a very consistent surface effect. Now, of course, abrasion techniques may or may not apply in your facility, and therefore you may be looking at this webinar today to learn more about the application of plasma. One other method of abrasion, however, the laser ablation, and it's actually an ablative method because that's the method that the laser uses to remove the matrix on the surface. You can see here's a panel done by DPSS Lasers Inc. They provided a panel to me where they did 6 different levels of ablation to the surface. You can barely see the ablation level here, where it has changed the matrix without getting to the fiber level. You might say the same thing about the second area here. It's about a 1 inch square, As you get into the third, fourth, fifth, and sixth level, they're actually getting down into the fiber itself. Once you're getting down to the fiber, you have changed the surface completely that you're trying to attach to. Remember that we want to attach to the matrix on the surface or a surface matrix resin that has a modulus that's compatible and a surface energy capability that's compatible with the adhesive that we want to apply. So laser ablation is another method that could be used as an abrasive method. They do have a linear system, an inline system available. But of course, when looking at the numbers, they're going to be very comparable to the abrasion numbers that we have here. We would probably have pretty low standard deviation with samples that are done with this type of technique. So that brings us to atmospheric plasma treatment. This is where chemical modification of the outermost surface of the substrate is done. It also cleans the surface. I have not talked about cleaning the surface, but you might notice in my previous matrix that everything was dry wiped and no solvents were used in this slide. Everything was dry wiped with a clean rimple cloth that has no binders. But the good thing about plasma treatment is that not only are you modifying the surface, you're changing the micro topography of the surface or the surface area, but you're also able to clean the surface without damaging the fibers. This creates select chemical groups on the surface of the material that actually enhance chemical bonding. And it can be adjusted using different gases to achieve exactly the relationship you want between the substrate material and the adhesive that you choose to use for bonding the substrates together. So with that, I'd like to turn this over to Ryan, and Ryan is going to talk about the plasma treatment. Ryan?
Thanks, Lou. Appreciate the background that you've provided here. Let's get into the first question about plasma. And the first question that we often get is, what is atmospheric plasma? Well, as I like to tell people, plasma is very simply an ionized gas. And when people talk about plasma, sometimes people will think about a technology known as vacuum plasma, in which you're batch treating samples, usually on a tray or some carrying device in an atmosphere, which is at vacuum. What we're going to be talking about today is atmospheric plasma, in that where we're creating this ionized gas in the standard atmosphere that your manufacturing environment would be in. So we're going to talk about a few different technologies today, and we're going to talk about what those technologies specifically do to the surface, as Lou began to allude to on his previous slide. The plasma treating process is going to do three things. It's going to clean, etch, and functionalize the surface. So when we talk about cleaning, what we're doing is we're actually removing organic and inorganic impurities from the surface. This is a piece which Lou mentioned, and as we dive into some of the research that we've done, we'll show some pretty impressive images later in the presentation about that cleaning specifically. When we talk to folks about the plasma treating process and we say it etches the surface, sometimes we'll get questions, ooh, is it going to damage the look of my part? Is it going to change what my customer sees? And what I like to tell folks is that if you're executing your plasma treating process correctly, you should see no change to the naked eye. Change that microscopically, and what you're going to see is that we've now etched the surface and created a significant number of additional bonding sites on whatever product you're producing. Finally, the third thing that we'll do to the surface is functionalize it. And this plays a role in some applications, not all, but essentially what we're going to do is we're going to increase the polar groups on the surface. This makes a difference in some applications, others it doesn't. Some cases we need to look at specific gases to use in the process as well, but functionalization is one of the 3 components that we do exact on the surface as well. So let's dive in to the different types of surface treating or plasma treating technologies that exist. We're going to talk about 4 of them today. And the first one is what's known as blown arc air plasma. Essentially what we're doing with the blown arc air plasma is we are putting a discharge between 2 electrodes and blowing that resulting arc out of that, which we're able to then pass a part through. This technology is very useful in a number of applications. It can be treated material for extruded, molded, formed, whatever it might be. One of the most important parts that you need to take into consideration for blown arc technologies is going to be the fact that it must be a non-conductive material. Given we're blowing an electrical arc across this, if you were to put a metal component or even a plastic molded component, potentially with metal inside it, and pass it through that arc, you would ultimately short that to that piece of metal. These applications typically range somewhere between 2 to 3.5 inches wide, depending on your application specifically. So it does allow you to treat a fairly sizable portion on many parts that are created. The second technology that I want to talk about is what's known as blown ion air plasma technology. This is a very flexible technology that now allows us to treat both conductive and non-conductive materials. The treatment width is a little bit different than blown arc. What we're doing with this technology is we're actually generating that plasma inside of the treatment head itself and blowing out the resulting ions that are produced in that process. That treatment is much more focused, typically somewhere in the neighborhood of about 1/2 inch wide. It does vary a little bit based on the speed and how close you are to the material itself. It's a very good technology for precise pattern or spot treatments. The picture that you see in the upper right is actually the back assembly component to a headlamp for your automobile. In this case, we're treating the glue track to enhance adhesion to make sure that that lens bonds and there's a watertight barrier in the headlamp. This is a technology that typically requires minimum dwell time. That means your throughput, whether you're running your parts down a conveyor or robotically moving the part or the head, is able to do this very quickly. Variable chemistry plasma is a technology that we'll introduce when we tend to find problems either with blown arc, blown ion, or the next technology we'll talk about, flame, when we're having difficulty getting treatment on those. With variable chemistry, what we're going to do is we're going to introduce a process gas. With blown arc and blown ion technologies, what we're really ionizing is the oxygen that comes in a supplied compressed air line. With variable chemistry, we add that process gas and ultimately functionalize the surface a bit different. This can come into play when maybe you have an adhesive that doesn't react well to that oxygen ionization that occurs, and you may need another gas, another formation to get stronger adhesion. Flame treatment is one of those that many people don't always associate with plasma, but it is one of those that we've put in our arsenal and tends to provide a very flexible application of a technology. Flame plasmas can be created with either natural gas or propane. They are very flexible in the fact that we can treat, from about 1.5 inches wide on the small side to significantly larger. We probably make, in the range of 10 to 20 inch wide, typically 500 millimeter wide burners on the upper end. So we're able to create a very flexible technology in widths, but also when it comes to contours of parts. What you see in the lower picture is a robotic application of flame treatment. We're treating the dash panel of a car typically either before it would be painted or a foam applied and then leather wrapped. But what the flame treatment does is it allows an active area or treatment zone of about 2 to 3 inches tall, which allows you to really treat some parts with contour very easily. It tends to be processed very quickly and have a long-lasting and uniform effect on the surface. So part of that flame treating technology is going to be the extremely safe and reliable gas mixing device that we've created. I know we'll talk to a lot of folks who will be concerned about having an open flame in their facilities, and gone are the days of having homemade flame treating systems that aren't as safe and have very simple designs. Both our gas control is extremely safe, but we've also advanced the burner technology that's used with this as well. We use a technology called drilled port burners, which allow extremely high velocity of the flame, allowing you to get that width, depth, and allow you to move that flame across the part while maintaining the integrity of that flame as well. So a quick summary of the technologies. Blown arc technology, again, is typically between 2 and 3.5 inches wide. Blown ion, you're typically around 1/2 inch. Variable chemistry, some standard solutions we have are in the 2.5 inch range, but those we really can make custom applications as well. And flame treating applications, again, have varied custom widths that we're able to look at for your application. Both flame and blown ion technologies are very flexible in that they can be used with both conductive and non-conductive materials. So how do you go about deciding which system and what integration method is right for your application? So one of the things that we always advise our customers or potential customers to do is make sure we walk through a process in which we look at the following things. What material is the part made of? Is it a simple plastic, maybe polyethylene, polypropylene, ABS? Is it something that's maybe a little more unique? Is it a carbon fiber reinforced plastic? Whatever it might be, we want to know what the material is, because we're able to tell which technology or technologies could be best. I talked about the conductive or non-conductive piece, again, very important. What do you want to treat? Is it the entire part, or do you just need to bond to a small area that we can isolate that plasma treatment on? We also want to think about how is the part going to be handled. We have folks that will present the part moving down a conveyor line, others that will present the part in any number of different ways. Ultimately, how fast do you want to run? What's the cycle time that you need to match your production run? All of these things we can test in our lab as well. We have a full-scale trial lab which features each of the technologies, and that is a service that we offer to all of our customers and potential customers for free as well. So Lou did a great job of talking about how you can test the materials. As I get into some details here, I just want to cover those again. Dyne level is one. It's a very simple, easy way to test surface energy. It is not always the best indicator. Sometimes you'll see a high dyne level where you don't get treatment, or a low dyne level where you do get good adhesion. Contact angle steps that up. Measuring the surface free energy and polarity on the surface is another advanced way that we talked about. Ultimately, you're going to look at the peel strength or some other sort of test that you're going to apply after whatever you're bonding to the surface includes as well. So we've done a number of tests on a variety of materials, and what we wanted to talk about here was some basic, very common materials that are used, plastics that are used. Here, polypropylene, polyethylene, PET. You'll see that many of those start out with a very low dyne level, low to mid 30s, something where you're not likely going to get good adhesion. You also see a correlation between that dyne level in these cases and typically a contact angle above 90. You'll remember that Lou mentioned a contact level above 90, you're not going to get proper wetting, and you ultimately are not going to get good adhesion. And you'll typically see lower surface free energy values as well. When you take those same materials and apply either blow-on ion or flame treating technologies, you see the dyne levels increase and contact angles by and large decrease as well as surface free energies increase. So we then took these and also looked at a few more unique or more advanced materials, PEEK, PEI. And what you'll see on these materials is that not all of them were as low on the dyne level as they started with. Some of them had a low contact angle under 90. You see that with the PEEK and the epoxy levels here. Well, when you apply blow-on arc and blow-on ion technologies, you see these dyne levels again increase. The contact angles are decreasing as well, and the surface free energy increase as well. Now, what was interesting as we went through and did these tests, we were trying to run them to see how high a levels could we get. When we measure dyne levels, the level 72 is what's known as water wet. We actually had to slow down the speed at which we processed these so we could get you some numbers that showed levels at which were readable. When we had these running a bit faster, we were getting water wet, very low contact angles, very high surface free energy. So we can really affect the surface pretty significantly on any of these materials that we see. We did the same thing with flame and variable chemistry, and you'll see here, I won't walk through all the results with you, but you'll see again, even at speeds of 100 feet per minute on flame, which tend to be pretty slow from a flame application, we do impact both dyne, contact angle, and surface free energy pretty significantly on these advanced materials. So one of the things that we looked at as we were running these results, and we were measuring the surface free energy with that Cruise surface analyzer. And what you'll see, what I want you to note here is not only essentially the droplet on the bottom left to the treated surface on the top, where that's really wetting out, but look at the two bottom pictures and look at the particles of dirt that you see on those bottom two pictures. As we look at the top two, which are treated, see how clean that surface is. So that is one of the effects, not only of the adhesion and the wetting out on this PEI material, but also how we are able to clean the surface. In this case, we used a variable chemistry plasma to exact these tests. One of the other tests that we've run is we've looked at bond strength. And this happened to be on a polyethylene surface, which we used a UV cured adhesive. We ran these tests after 24 hours. So we had a control component of polyethylene that was not treated, and then blown ion and flame treated systems as well. And what we saw is we saw a factor 3.5 times greater of bond strength on that polyethylene with that UV cured adhesive. So a pretty amazing change on bond strength with that technology. So I talked a little bit as we were talking about how you would select systems, what you want to think about. So other things you want to consider. Are you going to process these semi-automatically or offline? Will they be presented coming down a conveyor? Do you have existing equipment that you need to mount this equipment on? Are you going to use it robotically in some way, shape, or form? If you're going to use it robotically, are you going to keep the plasma treatment head stationary, or are you going to move that? Are you going to move the part? Whatever it might be, Or are you going to index it somehow? Many of our customers will use a indexing table like you see in the center picture towards the bottom there as well. Any number of ways that you can integrate these systems to meet your application requirements. We've seen a lot of advancement in plasma treaters over the last few years. One of our new technologies that's been released in 2015 have been our blown arc and blown ion series of systems. These are improving upon our first and second generation of machines and really taking advantage of technologies that we as Enercon use across all of the products that we support. We've developed new technology in the blown arc and blown ion systems as well. In addition to, we've added intuitive touchscreen controls, which in and of itself is exciting, interesting, but what it really does is it unlocks a plethora of options and features that just aren't available in many standard push-button controlled plasma treating systems. We've integrated multiple heads into these systems, so if you need to treat maybe 360 degrees around an object, multiple different components, or maybe you're trying to get a wider width by combining two heads together, what we're now able to do is have truly independent head control on those as well, which works really, really well in making sure you're able to run your application exactly how you want. In addition, we've put in plasma integrity monitoring, which makes sure if you want to take this control to a level of advancement, we can take you there as well. We've talked about a lot today in this webinar. Before we open it up to questions, we want to run through a quick summary of what we've talked about. So plasma and flame treating systems do three things to a surface. They clean, etch, and functionalize to ultimately improve your wettability and your ability to bond with coatings and adhesives. Some of the technologies that are available to you include blown arc, blown ion, flame, and variable chemistry plasma systems. You can apply plasma treatment on a variety of plastics, silicones, metals, glass, carbon fiber, composites, thermoset materials, and you may integrate these systems with robotics, indexing systems, integrated over an existing conveyor, or fixed position productions that you may have in place today. Now I want to turn it back over to Lou for a summary of what he shared with us.
Thank you, Ryan. Very good presentation. My summary goes back to the slides that I presented at the beginning, where achieving that surface-free energy, the raised surface-free energy value of the substrate so that it is higher, preferably much higher than that of the surface tension value of the liquid adhesive or film adhesive, is a necessity to getting that first stage of the chemical bond. Again, the goal of proper surface preparation is to not damage the fibers in a composite structure. And as you can see by the presentation that Ryan did, that can be achieved using the plasma system. Complete surface wetting is the first step to achieving that chemical bond, and most conventional abrasive surface prep techniques that we have demonstrated result in variable and inconsistent surface quality. And what the biggest variable there is operator. We do have other variables that fit into that picture, such as contaminants, so on and so forth, but we did not get into that discussion in this particular event. So with that, I would like to turn it over to our host and have some questions.
All right, great. Thanks, Lou, and thanks, Ryan. That was very interesting. I appreciate it. We do have quite a few questions, so why don't we just jump right into them right now. The first one is this: is it possible to over-treat thermoplastic surfaces when attempting to improve adhesion strength?
That's a great question. The answer to that is certainly yes, and that is a component where you want to trial the process, understand exactly what you need, whether you're measuring with dyne levels, contact angle, or surface free energy levels. You're going to want to go through a process where you find the right speed of the application, the right gap between the plasma treatment nozzle and your part, just to make sure your application does not overtreat.
Okay, great, thanks. Next question is this: is carbon fiber conductive enough to not work with blown arc and variable chemistry?
That's a component that we probably need to do a little bit more testing on. There's some possibilities that it will work. There's also some possibilities that it won't. So it is a component that we probably would have to take a look at the specific application and verify if we can use both a variable chemistry technology or blown arc technology.
Okay, great, thanks. Next question is this: can plasma surface treatment be applied to a plastic surface to get better adhesion for printing?
Most certainly. That is one of the applications that we tend to use plasma treating with. It's often used on plastics for decorating applications. We actually do a fair amount in the wire and cable industry to mark wire. So yeah, any sort of printing that you're looking at doing, we can help aid in that process.
Okay, great. Next question is this: how soon after treatment should bonding be performed?
That would be a question I would answer, and I would say that the sooner that you can apply and close the joint, apply the adhesive and close the joint, the better, so that the surface does not normalize. Obviously, these plastic surfaces have now just been energized, and they have a higher surface free energy than they did before. Therefore, now they are susceptible to contamination, to other types of materials normalizing that surface. If you're working with a metallic surface, oxidation would be a concern. But you know, the faster that you can get the adhesive spread and or applied and get the joint closed, the better.
Okay, great. Next question is this: the presentation discussed apparent increases in bond strength. Is that in reference to shear or peel?
I think that one's for you, Ryan. Was that yours? Mine was in shear. My numbers on the on all of the specimens that were abraded, those were all shear tests, and that's not pure shear. That's a lap shear coupon, which inherently has some edge effect. That's non-shear. But I believe that the testing done on the polyethylene is what you're referring to. So Ryan, would you have knowledge of that?
I'd have to go back and take a look at the exact test and specifically where, what method was used on that test.
Okay, and just to be clear, we are saving all these questions and contact information for our attendees. So any question that is not fully answered can be followed up on later. Next question is this: is this appropriate technology to bond dissimilar matrices such as vinyl ester and epoxy?
Yeah, I would say that yes. The surface that you're treating, if it's a vinyl ester surface or an epoxy surface, you're still in the same situation where you need to treat the surface so that you change that surface chemistry to allow for wetting of whatever adhesives that you're going to use. Even if you have a vinyl ester surface and you're applying an epoxy to that surface, that still needs to be treated. So it's applicable to any of these surfaces.
Okay, great. Next question is this: what is the improvement of plasma treatment on aluminum compared to phosphoric acid anodizing?
Ryan, you got any data?
You know, I don't have any data specifically comparing the two. You know, I will say that we do have success treating aluminum. It's many times it's ultimately a cleaning application. Typically, is what we're doing, and we do find success with it. Unfortunately, I don't know that we have any specific data comparing the two. But it would be something, you know, if there are tests that you want to run and test those two components, we'd be happy to help participate with that.
Okay, great. Next question is this. Do you have any adhesion data on titanium metal treated by plasma or flame? What is the treatment process condition you recommend?
Yeah, again, as we get into specific materials and applications, there are things that we've done, results that we have. Not always results that we can share. There are some confidentiality agreements around some of those, but they, again, are things that we can run specific tests and help you conduct those experiments.
Okay, next question is this. Are there substrates that don't respond well to plasma treatment? What about aerospace composite resins, including BMIs and cyanate esters?
I would think that all of these would fall into the same category. Any of these thermoset resins or thermoplastics are going to there's going to be an advantage by selecting the proper plasma methodology and perhaps even the chemistry in order to achieve the best bond to that particular surface. There's not much difference between those surfaces, the BMI, the bismuth, the bismuth amide, the epoxy, some of the newer materials that are out there. You're going to see a slight difference in the end chemistry that you want to attach to, and that might precipitate looking at a chemical solution, so a chemical plasma adjustment using some kind of gas for the plasma. But they're all going to react in a similar method, and of course you're going to gain the surface free energy that you're looking for in order to get the wetting, to get the good bond, even with those higher temp materials that you mentioned.
Okay, great. Next question is this. Is there a process available to apply treatment simultaneously to a very large area? It seems like the processes covered here are for relatively small areas.
There are ways indeed that you can cover large areas. I think we'd have to define specifically what large is. What will typically be involved, as we've worked with things like automobile components such as bumpers, dash panels, door panels, the likes of those, so something size-wise that people can relate with. Those are going to be pieces where we're going to use one or more treatment heads, and you're going to move them robotically in some way, shape, or form across the part.
Okay. We're coming up to the top of the hour, so we're going to take one more question, and that is this. Between flame and plasma treatment, which is the most effective process for treating carbon fiber?
Ultimately, it's going to depend on your end use, what you're looking to accomplish. Both may be effective. To say one is more effective than another, it would really depend. We try not to go to that level and say one is better than the other. The second we do that, we're going to find another application where we find out the opposite is true. So we always try to ask folks to come to the table when they're looking to run samples or run a trial, take part in some tests, to come in with an open mind as far as which technology is right for them. It's not always going to be one or the other. Sometimes it might be more than one, sometimes it might only be one. So that's the biggest piece that we ask folks to make sure they bring an open mind to the testing process.
Okay. Well, we are at the top of the hour, so I want to bring this webinar to a close. I do want to remind everyone that you'll be receiving an email from Composites World with a link to a recording of this presentation. If you want this presentation in PDF form, it is available from our presenters, and their email addresses are on your screen right now. I encourage you to contact them if you want more information. We also do have many questions that we were not able to answer today, so I'm sorry we ran out of time, but the questions will be saved, and I hope you can get some follow-up from Aberus and Enercon after this is over. So I want to thank everybody for coming, and Lou and Ryan, I want to thank you for presenting today. It was very interesting.
Okay, thank you. Thanks to all that attended.
All right, guys. Thank you. Have a good day.